We're going to talk a little bit about shorthand notation for electric configuration. It's an easier way that we can write the electron configurations. Now it's important to know these electron configurations because electrons are the key when it comes to chemistry. That's what bonds we've talked about. Now you can look on page 166 at the groups to figure out the electron configurations. But we're going to go over them as well. Now there's a shorthand notation we'll use, and the thing is it uses electron configurations of the noble gases for the other electron configurations. Example, for sodium, instead of writing this long 1s2, 2s2, 2p6, 3s1, the shorthand notation is just fluorine 3s1. So we go back to the preceding noble gas, then we write what comes next. And we'll show you many examples of this. First, we need to know what the blocks represent. Now this part of the periodic table is the p block. That means the last energy levels are the p, or the last orbitals would be the p's. All of these have electrons or valence electrons in the p orbitals. So anything that ends up here, any element in here will have their very last valence electrons in the p orbital. And the transition elements here, all of these have valence electrons in the d block. Over here, alkali, alkaline earth, groups 1 and 2, their valence electrons end in the s block. The intertransition or rare earth, their f. Their valence electrons are in the f block. So more specifically, here we have the p's, d's, s's, and f's. But in addition, we also have the energy level, this row. So whatever row will tell you what their energy level is, their last valence energy level. Anything here, their last valence energy level is 1s. That really only means hydrogen and helium. That's their outside electron configuration ending in 1s. These are in the second row, second energy level. So this would be 2s. These guys would be 2p. The third row, their valence electrons would be in 3s, and these guys, their valence electrons would be in 3p. Their valence electrons would be in 4s, and these guys in 4p. Now notice, it's important here to note that transition elements, they don't keep up with the 4s. It goes from 4s to 3d, then to 4p. Now if you remember when you wrote your electron configurations or you did your off-bow diagrams, it skipped when you were placing those electrons, it skipped from 4s, then it went to 3d, then back to 4p. Right, this is where we can see it on the periodic table. But just know, once you fill up the 4s, then you go to the 3d and then the 4p. After that, these electrons, these valence electrons are in the 5s. These valence electrons are in the 4d. These are in the 5p. Now these guys, their valence electrons would be in the f, the 4f and the 5f. Notice after the 6s, you go to the 4f. After the 7s, you go to the 5f. And the f's, if you remember, hold 14 electrons. Now here are some periodic tables that show the exact electron configuration. These electron configurations are only showing the outside electron configurations because that's the only ones that matter. Helium is 1s2, 2p6, argon is 3p6, krypton 4p6, xenon 5p6, 6p6. So notice these are all p6 except helium is s2. So that's the exception, but these are all P6s. Now look over here, these are P's, but P5, P4 over here, P3, P2, P1. Knowing that what row it in, like 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. Down here, 6p1, 6p2, 6p3, 6p4, 6p5, 6p6. So these all have one electron in their p shell. These guys are 2s1, 2s2, 3s1, 3s2, 4s1, 4s2, 5s1, 5s2. So it goes by row. Notice the row it's in. Again, the transition are different. This is 3s1, 4s2. So I mentioned before that you can write, even though you fill up the s orbitals first, you can write 3d then 4s. And in fact, that would probably be the preferred way to do it. As we go through, they're all 4s2 because we filled up the 4s2s. But then this one is 3d1, 3d2, 3d3, 3d5. Now, there are some exceptions, as we've talked about. So they don't follow the exact rule. So in general, though, we're just going to follow the general rule. You don't have to really know the exceptions, but just know that they exist. So this should be 3d1, 3d2, 3d3, 3d4, 3d5, just regarding any exceptions. 3d6, 3d7, 3d8, 3d10 should be, if we were counting, 3d9, but then 3d10, 4s2. Here, the last energy level is the F, but we can also count, we can put the S at the end because that's really the bonding orbital. Now these all have 6s2, but this is F1, F3. Again, there's our exceptions. F4, F5, F6, all the way up to F14. Here's another periodic table to look for it. So these are all 2p's. 3p's, 4p's, 3d's, 4d's, etc. So this is really just more of the same. So it's important that you know 1, 2, 3, 4, 5, 6, 7, S. Now, all you have to do is count the row, 1, 2, 3, 4, 5, 6, 7, as well as over here, 2, 3, 4, 5, 6, 7, here's 1. Now, again, the transition go down to 3, 4, 5, 6, and the F blocks start at 4 and 5. So let's try some of this. This is actually can be very fun. Again, something you can try at your parties. Get a group of friends together. In fact, there's a dance coming up, charity ball. I recommend you bring in a periodic table, pad of paper, and say, okay guys, forget the dancing, let's do some electron configurations. Beryllium. Now, we know that this level this part is the S's. So how we do this, we go back to the previous noble gas. What's the previous noble gas? That's helium. So to write beryllium, we put helium in parentheses. So that means anything, all that electron configuration before that noble gas is just inside, we don't have to report on it. Then we go to, this is the S block. What row is it in? It's in row 2, and it's 1, 2 over. So it's in the, if it's in this block, it's the S block, and it's 2 electrons. There's 2 electrons in there. So that's beryllium. Okay, so let's try carbon. Carbon is here. This, remember, is P. So these are all the P orbitals. It is in the p orbital. We start here at 1, 2. And what row is it? It's row 2 still. So what we have to do, though, is we start at the helium, the last noble gas, and then we have to go here. That's going to be 2, row 2. Now it fills up the S's, so that's 2s2. Then we go to the P, row 2 still, P, 1, 2. So it's 2s2, 2p2. And this shows the second energy level 2, and it's the orbitals of S and P. Now, how many total valence electrons does it have? It has 4 valence electrons. So important, the SP, or really the main ones involved in bonding, has 4 valence electrons and the second energy level of S and P. Let's try another one. Let's try magnesium, Mg. Now the previous noble gas is neon. So we put neon in brackets. And now magnesium is in the 3rd energy level, and it is in the S orbitals, and it has 2. It's in position 2. 1, 2. So 3rd energy level, S orbital, 2 in the S orbital. So this one has 2 valence electrons. One of the important things about the electron configuration in the shorthand is it just shows the valence electrons. Chlorine is atomic number 17. It's in the P block, and then it's in row 3. So the previous is neon, previous noble gas. Now we have to start at the right after neon. It goes and fills up 3rd energy level. We start the 3rd energy level and we go to S. Fills up 1, 2, 2, then we go all the way over here, and this is P, so it's still in the 3rd energy level, 3P, 1, 2, 3, 4, 5, P5. So electron configuration for chlorine is neon, 3s2, 3p5, 3rd energy level, S and P. Combined they have 7 valence electrons. Of course, it's in group 7 anyway. So vanadium, circled there. So we're going to go to the previous noble gas, which is argon. Start here. K, so this is row 4. So energy level 4. S fills up the 1 and the 2, 4s2. Then it goes to the D. You see we just go to the D. But remember, it goes from 3D now. 3D, 1, 2, 3. 3D, 3. But we're going to rewrite it as argon. Let's try selenium, and so you guys should be trying this as well. See if you can pause this, figure it out, and then see if you get the right answer. So we go to the previous noble gas, it's going to be argon. Then we go to row 4. We're at row 4. We fill up the S's, 1, 2. It fills up the D's. So the D's will fill up, as we know. D holds 10 electrons, it fills up the D. Then we go back to the 4 level, but this is P block, 4P, 1, 2, 3, 4, 4P4. And we can rewrite it as 3D10, 4S2, 4P4. And notice sp orbital has 6, 2 plus 4, 6 valence electrons. Okay, let's try one more. Thallium, Tl. So we have to go to the previous noble gas, xenon. So it's xenon, then we go all the way here, cesium. So that's row 6, period 6. S, it fills up the S, 1, 2. Fills up the D's at 10, 3, well, not 3. So what D is it? This is 3, this is 4, this is 5. So it's 5D10. Now this still goes back to 6. This is the P block. So it's 6P1. And we could rewrite it as xenon 5D10, 6s2, 6p1. Notice we have 3 valence electrons, which makes sense. It's in the 3rd, or group 3A, going up and down.